For question 2, we're asked to find a unit normal vector to the surface defined by the equation x times y times z equals 16 at the point P with coordinates -2, 2, and -4. And then we want to determine the equation of the tangent plane at P. And I guess technically we've got a couple of ways we could do this. We know that we can't, because when it comes to finding a normal vector, we can use the gradient to get that. And you could do that here, but equally, because this surface can very straightforwardly be written in terms of a function z equals f of x comma y, we can also just use that function and its corresponding partial derivatives. That's the approach I'm going to take, but ultimately it's the same thing. It really won't change many of the details of what we do here. All right, so I'm going to write this as, first of all, z equals 16 over x times y. So that's going to be my function f of x comma y. In order to get the normal vector, not necessarily a unit normal vector, mind you, just a normal vector, we can write this as the vector composed of the partial of f with respect to x at P, the partial of f with respect to y at P, and -1 as the z component, or negative the partial of f with respect to x, negative the partial of f with respect to y, and +1. Ultimately, those are both normal vectors. They're just pointing in opposite directions. I tend to use the first of those when I'm working with normals of planes and trying to find tangent planes, the kind of stuff this question is asking. I tend to use the other version, the version with +1 as the z component when I'm working with things like surface integrals, because that's going to give me an upward pointing normal to a surface, which is typically what I want in those problems. So let's see. Either way, the partial of f with respect to x in this case, well, that's, of course, I treat y as a constant. So that's going to be -16 over x squared y. And very similarly, the partial of f with respect to y will be -16 over xy squared. So at the particular point that we're interested in, x is -2 and y is +2. So the partial with respect to x then is going to be -16 over, let's see, 4 times 2 is 8, so that's -2. And the partial with respect to y at -2 comma 2, that's going to be, let's see, it's going to be -16 divided by -2 times 4, so that's -8, which gives me +2. So a normal then, and again, we're looking for a unit normal, we'll get to that in a moment, to the surface is the vector n with components -2, +2, and -1. Or +2, -2, +1. Again, works just as well. Now that's definitely not a unit normal vector, but to get the unit normal vector, we just have to find its norm and divide it by it. So the norm of n in this case is going to be the square root of -2 squared plus 2 squared plus -1 squared, which is the square root of 4 plus 4 plus 1 is 9. Square root of 9 is 3. So a unit normal vector is given by, I'll call this capital N. That's going to be the original normal little n divided by the norm of little n. So that's going to be -2/3, +2/3, and -1/3. Okay. Then we want to determine the equation of the tangent plane at P. And really, we could use the unit normal to do that, or we could use, and it's probably slightly easier to use the original normal that we found for this purpose, just because we don't have to deal with fractions then. So the equation of the tangent plane well, in general, that's given by a normal, So again, the first normal, the unit normal, they're all good. Dotted with any vector x in the plane minus a particular vector x naught in the plane. That's x naught in the plane, not x not in the plane. You know what I'm talking about. Equal to 0. So if I do use my original normal that I found then, that's going to be the vector minus 2, 2 minus 1, dotted with, well, using the point P, that's going to be x minus minus 2, so x plus 2, y minus 2, and then z minus minus 4, so z plus 4. That dot product's got to be equal to 0. So that's going to give me negative 2 times x plus 2, plus 2 times y minus 2, minus 1 times z plus 4 equals 0. And then I certainly want to clean that up. So that's going to give me negative 2x plus 2y minus z. Let's see, my constants on the left-hand side right now are minus 4, minus another 4 is minus 8, minus another 4 is minus 12, and then when I bring that over to the right-hand side, it's positive 12. So I could write that as minus 2x plus 2y minus z equals 12. I could write it as 2x minus 2y plus z equals negative 12, or any constant multiple of either of those equations. They'd all be legitimate answers in this case. That's question 2. We'll move right along.